So it looks pretty messy on the screen, but we're gonna keep it going. Let's change the problem. Let's just say that this person is pulling the cart, but the let's say that the wheels broke. Let's say that there are no wheels. Let's say we're pulling at the same angle. Let's say it's the same mass, but we have no wheels, and so now we are dealing with a frictional force. And that frictional force is pointing backwards. Let's say we are moving. So let's say we at least know that we're kinetic friction. And let's say that the mu is equal to 0.100. So let's say the problem gave us the mu. Now, mu isn't the force. Mu will help us find the frictional force, but mu is not the force. So don't think that mu is actually equal to the force. That's not the case. But we're just saying the surface, between the surface and the object have a mu of 0.1. So that keeps a good portion of this problem the same. If we keep it this way, right? So it's the same pulling force, it's the same gravity, it's the same normal force even, because those aren't affected by the friction. Because friction's, as you can see, is friction's in the pure x direction, but that does affect the x motion. So now we have to redo all of this. The rest of it is fine. The rest of it is as it was. But this is all gone. I have to restart the x analysis. Summation of the forces in the x direction equals 0. No, not 0 necessarily. Equal ma. Let's say again that we're assuming that we have enough force to keep this thing moving and accelerating. We don't know that, but that's an assumption that we're going to make. If we find that it's a bad assumption, we'll alter it. So if I look at this, well, I still have my positive pulling force. But now I'm going to have the force of friction. And that's going to equal ma. We think it's going to equal ma. And again, I had found the pulling force earlier. That was 80. I need the force of friction. Now, I can do it in line or I can do it off to the side. I'm going to actually do it off to the side this time. So we know that force of friction kinetic, and it's kinetic, so it's equal. So it's not that range, right? When it's kinetic, it's only got the one value, mu k Fn. And I guess I really should have put up here that this was mu k, huh? Okay. Well, 0.100 times the normal force. Again, the normal force is not equal to the weight. That means that we do not have as much friction in this scenario as if the object was just being pulled sideways. Because again, this force here pulled over and upward. And so when it pulled upward, it actually helped reduce kind of like the pressure, if you will, of the box against the floor. And so if you pull upward a little bit and reduce that normal force, you're going to reduce friction. Now, in the previous video, I did make mention that what if, and it's not in this picture, and I know it's a lot going on, but what if we were to push the crate over, but also push it downward as we pushed it, well, then that would make the normal force actually go up. And that then would make friction go up too. Because if I push over and downward, the floor has to support not only the gravity, but also that extra downward force. And that would make the floor have to push back even more. And so if you're pushing at an angle, you're trying to move the object horizontally. If you pull it over and upward, it reduces the normal force. If you push it over and downward, it increases the normal force. And that could affect friction. All daisy chains together. So in this very specific case, the normal force here was reduced because the pushing force also helped support the object, helped lift it up a little bit, if you will. And, sorry. And so this, if I multiply it out, is 13.62 with 13.6. All right, so the frictional force is not that tremendous here because I have a very low mu. And we said the mass was 20. Acceleration. So when I subtract these, then that's what, 66.4. Divide that by 20. All right, so .32. And no, this better be less than the previous answer of 4 because, you know, we got a little friction, so it's going to try to slow us down a little bit. So, a lot going on, but I hope that all made sense. And trust me, we're going to get lots of practice on these. We do have another kind of problem where objects are sliding up or down a ramp, but that will be for another day. All right, so try some of these problems. Start getting used to them. Fun times again.